So what do we got that we're dealing with today?
I have a quiz tomorrow on the intermediate value theorem
Okay.
in chapter or lesson 1.5 in the calculus book.
Okay. You have some exercises. Let's just talk about the intermediate value theorem for a moment.
Okay.
It says that if I have a continuous function between A and point B, and f of A is that, and f of B is that, there's no way you can get from A to B without traveling through all points in between. Similar to saying that if you got in your car and sped up from 30 miles an hour to 60 miles an hour, you would not be able to avoid going through 50 miles an hour. You can't jump over. The intermediate value theorem is more, it's called kind of a theorem of existence. I'm not sure how many problems you can actually prove by the intermediate value theorem. It's used a lot to prove other theorems. But basically it says, and the function has to be continuous. In other words, if I take a function like this, then clearly I don't ever go through those values when I go from point A to point B. In other words, because this function is not continuous there. So we're able to skip over that. But if you have a continuous function, then you have to go through all values of f of x between f of A and f of B. All right, which problems do they want you to do here?
You didn't assign any.
They didn't assign any problems to you?
No.
Well, that's because there's not a whole lot of problems that you can assign to illustrate or figure out the intermediate value theorem. Let's see, that's the last chapter, right, in your book also, 1.5?
Oh no, 1.5.
Yeah. So you're just about ready to get into differentiation. So you scheduled a half an hour today because you weren't quite sure that you understood the intermediate value theorem, or?
And 1.52, mostly just with the proving.
With the what?
I found the problem for the.
They didn't. They haven't gone through the epsilon delta definition of limit, I hope.
No.
Yeah, that's beyond the scope of a first-year calculus student. I don't know why they put it in the books. That might be one of the hardest things to understand in all of calculus, is that epsilon delta definition of limit.
Oh yeah.
So I'm glad they skipped that. What were you saying?
I found a problem for the intermediate value theorem.
Okay, cool. Can you verbalize it?
Yeah.
Okay.
Prove that the function f of x equals negative x to the fourth minus 3x plus 6 has a 0 on the interval -1, 2.
Now, the thing about polynomials, they're always continuous. Okay, so we know that just because this is a polynomial that it's continuous. Okay, not necessarily true for a rational quotient. If I had x plus 1 divided by x minus 1, that's not continuous. It's not continuous where x is 1. Okay, so this is the function, this is the interval. What do they want to know?
They want to prove that it's continuous.
They want to prove that it's continuous. Wow. Is there an example that they give you on proving continuity based on the intermediate value theorem? I just read this chapter. Here's an application. Use the intermediate value theorem to show that the polynomial function has a 0 in the interval 0 to 1. So I guess that's what we have to, no, this doesn't quite say that. So they want you to prove this is continuous, not that it has a 0 in that interval. Is that correct?
Yeah. Here's an example problem that he gave us.
Okay, what page is that on? Oh, that he gave you. Okay, let's look at that.
So the problem is f of x equals x squared minus 2 minus cosine x.
Minus 2 minus cosine x?
Mm-hmm.
Like that? Okay.
And the interval is 0 to pi.
Okay, let me guess what the first step is. Evaluate f of 0, and the second step is to evaluate f of pi?
Yeah.
Okay. F of 0 is what?
0 squared minus 2 minus cosine of 0.
What's cosine of 0?
1.
Okay, so we got minus 2 minus 1, so that's minus 3. F of pi is pi squared minus 2 minus the cosine of pi, which is what?
8.869.
No, give it to me. Actually, it's not. Cosine of pi is -1.
Oh, right.
Here's what the cosine curve looks like. And there's pi right there. And that's -1, and that's +1. So the cosine of pi is -1. So this answer is pi squared minus 1. That's what f of pi is. Now, I have no idea what the next step might be. What, in his example, what does he do now to prove that this thing is continuous between those 2 points?
He had a verbal answer. He said, since f of 0 is less than 0 is less than f of pi, the intermediate value theorem states that the value of c lies within the interval 0 to pi such that f of c equals 0.
Okay. That's kind of the same as example 7 on page 76. Oh, no, excuse me, not example 7. Example 8 on page 78. In other words, what he's saying is he doesn't really prove continuity, what he said. That doesn't prove continuity at all. what it proves is that f of 0 is negative, f of pi is positive, so the function on that interval, 0 to pi, goes from a negative to a positive, something like that. And what he proved with that verbal statement was that there is some point where it has to cross the x-axis. In other words, it cannot get from negative to positive without crossing the x-axis as long as it's continuous. But proving that there's a 0 does not prove continuity. I mean, what if this function did this?
Yeah.
In other words, it would still, f of 0 would be negative, f of pi would be positive, and it would not be continuous. So, not quite sure how you prove continuity here. Let me say something about continuity. In proving continuity at every single point, the book tells you that all polynomials are continuous on the whole real number line.
Yeah.
The one thing, the odd thing is that, yeah, they shouldn't be giving you intermediate value theorem at this point. I don't think. I think that's a mistake. Because the one way I could prove that this was continuous is if I can differentiate it. In other words, if I can differentiate it over the entire interval, then that proves continuity. And that's the best way to prove continuity. There might be a way with this intermediate value theorem, but I don't think he has proved it at all with his explanation. And whether we use this second function you gave me, the example, or whether we go back and use that one, the top one, well, I can certainly figure out, his process is going to be figure out f of minus 1. Let's do that. That's negative 1 plus 3 plus 6, that's 8. And let's figure out f of 2. I hope I don't make a mistake here. That's minus 16 minus 6, that's minus 22, plus 6, that's 16. So, okay, I can say f of minus 1 is less than c, which is less than f of 2. So there's certainly some c between f of minus 1 and f of 2, assuming that's continuous. But we know that's continuous merely because all polynomials are continuous on the entire real number line. But how you prove continuity is another story altogether. I don't know. I can see why you scheduled a session because it's not clear at all. And, you know, this is, okay, here's example 7, testing for continuity. That doesn't help a whole lot. Page 76, we can at least talk about continuity.
Okay.
Example 7, where they have 3 different functions. Tan x, the first one, the graph of it is at the lower left part of the page. You can see from that graph that it's continuous wherever the domain is defined. Now, there's a vertical asymptote every pi. So the domain is not defined at minus pi over 2, plus pi over 2, plus 3 pi over 2, and so forth. But it's continuous on its domain. That's notice what it says down there on the lower left. F is continuous on each open interval in its domain. Number B is a really weird looking function, the sine of 1 over x, which the function is equal to the sine of 1 over x as long as x is not equal to 0, because clearly it wouldn't be defined there. But then it tells you that it's actually equal to 0 when x is equal to 0. And the answer says because it's continuous except at x equals 0, yeah, even their answer. See their answer for B, for the solution?
Yeah.
It's not exactly logical, I don't think.
Yeah.
It says it's continuous except at x equals 0, and the sine function is continuous for all real values of x. It follows that y equals sine of 1 over x is continuous at all real values except x equals 0. Well, I'm not sure how they come up to that, because at x equals 0, the limit does not exist. Okay. Okay. So this has to do with limits existing at all points. In other words, they're saying the graph at the bottom, B, is not continuous, even though it kind of looks like it does. It is,
Yeah.
right? I mean, I feel like I could draw that with a pencil and I would never have to lift up my pencil.
Yeah.
But the reason it's not continuous is because at 0, the limit from the left is not the same as the limit from the right. And so they list its continuity as negative infinity to 0 and 0 to infinity. But they don't really say why it's not continuous at 0.
Yeah.
Yeah, getting into this level of calculus and the Squeeze theorem is a little silly in my opinion. It really is. I don't mean to understate the importance of it. It's certainly important. It's just not what should be being given calculus students at this point in their calculus career. It's demoralizing, it's complicated, it's not explained well here in the book, so why even put it in? And then notice the difference between B and C. C is very similar function. It's also not defined at x equals 0, and it's a piecewise function where they say, okay, at x equals 0, we're going to let it be 0. And look at the graph in the lower right. And that thing is continuous on the entire real number line. Question is, why is that continuous at 0 and the other one is not?
Yeah,
And that has to do with something they call the Squeeze Theorem. And the Squeeze Theorem is if you have two functions and a third function that is at all points less than the top function and greater than the bottom function. And the top function goes to a limit of, say, 0 at 0, and the bottom function goes to a limit of 0 at 0, then anything that is always less than the top function or greater than the bottom function has to go to 0 at 0 also. Even though you can't necessarily prove it, it's true. Look, well, yeah. In other words, the way you prove it is by using the Squeeze theorem. If you look at their explanation under C, they say that it's just like B, except that the oscillations are dampened by the factor x. See, what's going on in B is that the oscillations, the frequency is getting smaller and smaller and smaller as you get to 0. Notice how the period gets small. You know what the period is, right?
Yeah.
For a sine function or a cosine function. It's the period, it's the interval between peaks, basically. And that interval is actually approaching 0 in problem B. And that's why it's not continuous at 0, is because the period is approaching 0 also. And in number C, wow, notice in their explanation for C, they use the bottom function is negative absolute value of x. The top function is absolute value of x, and that's the way the graph shows it. In other words, the gray V at the top is the absolute value of x. The gray V below the x-axis is negative absolute value of x. Well, we know that absolute value of x does approach 0 from the left and the right on both functions, right? On negative absolute value of x and absolute value of x. And because it approaches 0, we can say it has a limit of 0. And what else we also know is that x, the middle function, x times sine of 1 over x, is always greater than or equal to negative absolute value of x, and it's always less than or equal to absolute value of x. In other words, it is always in between those two functions. Therefore, at 0, it has to exist. The limit has to be 0 at x equals 0. And that's the reason it's continuous, is because of the squeeze theorem. Notice that you cannot say the same about sine of 1 over x. It is not always, in other words, number B, which is not continuous at 0, is not greater than negative absolute value of x and less than absolute value of x. I hate even talking about it because I feel like I'm just confusing you with every word I say. These are extremely sophisticated principles. And let me assure you that as soon as you get to chapter 2, everything's going to get a lot easier.
Okay.
Okay? Just don't get demoralized. Whether you understand this stuff or not, don't get demoralized.
Okay.
I have never quite understood why math works this way. And it doesn't matter whether you're talking geometry. They start you off with proofs, which you'll remember is probably the toughest part of geometry.
Yeah.
In Algebra 2, they start you off with linear programming, which is probably the toughest part of Algebra 2.
Yeah.
With trig, they even start you off tough there because they start you off trying to explain how what radians mean and how to convert angular velocity to linear velocity. That's tough stuff. So I would say even trig starts you off with super tough material. In calculus, start you off with, are you kidding me, in chapter 1, the epsilon delta definition?
Yeah.
If you want to really understand that, not that you do because you're not going to cover it, I would go to Saul Kahn's, are you familiar with Khan Academy?
Yeah.
He's got a wonderful 10-minute explanation on the epsilon delta definition of a limit. And in that explanation, which is really quite great, he's a terrific teacher, maybe the best in history. He makes the statement that this is not, shouldn't be covered by first-year calculus students. It's beyond first-year calculus students. And yet they insist, I about once a year I get somebody that has questions regarding the epsilon delta definition, and they're just starting calculus. Makes me ill almost to see such bad teaching. But don't get me wrong, I'm a huge fan of the authors of this book, Larson, Hostetler, and Edwards. So far be it from me to criticize them. Yeah, I'm not sure there's much more to be said for the intermediate value theorem. As long as you understand it conceptually, and it is an existence theorem, meaning it's used really to prove other theorems. Yeah. Just looking at the back of this chapter, or even 1.4. And that's where this comes up, is in 1.4. I notice some of the problems, like 55, where they say, is the function continuous on the entire real line? Explain. Well, gosh, I didn't see any application at all that proved continuity other than this bisection method. Has he taught you that?
No.
No, I've never learned that either. I suspect that might be part of actually understanding how you prove something is continuous on the entire number line.
Yeah, I think.
Because the examples they give don't do that. The examples they give, well, the only thing they even come close to giving is example 7 on page 76, testing for continuity. And they don't by any means prove that it's, they don't give you much proof. Oh, I don't know what to tell you, Brianna. Don't get demoralized. In section 1.5, going beyond the intermediate value theorem, even that. The best way, if you look at 84, page 84, example 1, if you look at those 4 graphs on the bottom, it's pretty easy to figure out infinite limits, right?
Yeah.
In other words, as we approach on the left, as we approach 1 from the right, it goes to positive infinity. As we approach 1 from the left, it goes to negative infinity. Therefore, what's the limit at 1?
It doesn't exist.
Correct. Look at number 2, that second graph. We're going to approach positive infinity as we approach 1 from the right, and we're going to approach negative infinity, positive infinity as we approach 1 from the left. Therefore, what's the limit at 1?
Positive infinity.
Yeah. That's, in other words, the number 1 rule for limits is the limit from the left has to be exactly the same as the limit from the right for it to even exist. And they don't in graphs A and C, and they do in graphs B and D. Even though the answers are positive and negative infinity, that's still a allowable limit.
Yeah.
All right. I guess we can end it there. I don't feel like I've helped you much today on this topic, but like I said, if you can get to chapter 2, everything's going to get easier.
Awesome.
Even though it might not look like it at first. Even chapter 2, the definition of first derivative, they give you the hardest possible one to start off with rather than the easy one. It's like they're teaching you how to ski and they're dropping you on the expert slope to start instead of the beginner slope. That's my viewpoint of it. And I totally disagree with it, but every student, if you can just get them past that initial super tough stuff, then you can get into stuff where far more understandable.
Okay.
Okay? All right, Brianna, I will talk to you next time, and good luck.
Thank you.
You're welcome. Bye-bye.
Bye.